Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Previously, I wrote a free list container which had a vector as its buffer, and I ran into the problem of conflicting destruction of items, which made it necessary to write our own vector container that has an extra template parameter to control whether the items should be destructed upon deletion or not. I stopped halfway of writing the vector class, and today I'm going to finish it and use it for the free list. The next two functions that I'm going to write are the two overloads of resize function. Because we are going to resize the buffer and initialize all the items in that buffer with the default constructor, that means that the data type used in this vector should be default constructible. And we can assert that using this static assert. Here, if the new size is larger than the actual size that we have, we need to reserve more memory. And if the new size is less than the actual size, we are going to destruct the rest of the items beyond this new size. And otherwise, we do nothing. So if the required new size is larger than the size that we have right now, we need to reserve memory for new size and then initialize the rest of the buffer with default values of the data type that we are using just by calling mplaceBack. And if new size is less than size, we go and destruct this range between new size and size if the struct is true as template argument. Otherwise, this part of the code will be excluded anyway. Then we can write the overloaded one. In this case, because we are copying this value to all items, then it should be copy constructible, and we can check this by using this construct in the standard library. And the rest of the function is pretty much the same, except that we now have to use this value to copy construct the new items in the rest of the array. Next, we need to write the implementation for reserve. And reserve will allocate memory to contain a specified number of items. I'm using realloc here instead of malloc or new because it will try to reallocate enough space to fit data and the new capacity. So if the memory region where this data resides can be expanded, then realloc will just expand that memory and therefore the data won't be copied over to a new location. But if that region can't be expanded, realloc will allocate a new region of memory that's big enough and then automatically copy this data over to that new memory location. And that way we don't need to explicitly copy any data whenever we allocate new memory. Here we assert that this memory allocation succeeded. And if we have a new pointer to a new buffer, then we can update the pointer to this data by casting this new buffer to our data type and set the new capacity as well. If the new capacity is less than or equal to the old capacity, we do nothing. I think we now have all the functions that we used here, except mplaceBack, and that's the function that I'll be writing next. Here I'm using the same function signature as the standard libraries vector, which accepts a list of optional constructor parameters, if any, and it will also return a reference to the newly constructed item. If we don't have enough room to put a new item in the array, we reserve new memory, and each time that we have to allocate new memory, we reserve 50% more than what we had. And that way we can minimize the number of allocations per inserted item. Next, we use displacement new to construct a new instance of t at the end of the array. Then we increase the size and return a reference to the newly created item. And then using this function, we can implement the other famous function from vector, which is pushback. There are two versions of pushback. One adds a new item at the end of array by copying a value, and the other one adds a new item at the end of the array by moving a value. And then we need to write the erase functions. Here we have the erase function, which takes a pointer to an item that we would like to remove. Then it will do some checks to see if that item is within the range of the array. And if we need to destruct the item, then it will call the destructor of that item, decrease the size, and then move all the items after this item up by 1. So this item will be overwritten by the following data. And of course, we only copy the data if this item wasn't the last item in the array. And similar to what the erase function in the standard libraries vector does, we return a pointer to the location where the moved items reside, which is basically just the old address of this item. Now, in addition to these two erase functions, I'll write an erase function that's in theory faster because it removes an item by only copying the last item in the array to its location and thus overwriting it. It doesn't preserve the order of items, so if that's important, the regular erase function should be used instead. In this case, we do all the things that we did before for regular erase, but instead of moving everything after this location up by 1, we just copy the last item from the end of the array to the item that we want to remove. The next function that I'm going to write is the swap function, which swaps two vectors. This is a standard swap, which puts the other vector in a temporary and then assign this one to the other vector and the temporary to this one. And the rest of the functions that I would like to write are only the accessors, either to the data in this vector or to the items themselves. So obviously I'm not going to implement all the functions that the standard libraries vector has, but I will write the functions that access the data. The first two functions return the pointer to the start of the data buffer. And the empty function indicates whether this vector is empty, obviously, and the size returns the number of elements in this array. And we have one more function that returns the current capacity of the vector. Next, I'm going to write the bracket operators for accessing the items within the data buffer. This indexing operator returns the item at this specified index, and there is also the constant version of it. Next, we have the front and back functions. So the front function returns a reference to the first item in the array, and the back functions will return a reference to the last item in the array. If the array is empty or there is no data allocated yet, then it will cause an access violation and the application will crash. And finally, we have the begin and end functions. These functions return pointers to the start of the buffer and a pointer that's one past the last element in the buffer. Calling such a function will result in an access violation when data is a null pointer because there has been no allocation. So I'll add an assertion to check for this situation. And I think that's all we need to write to replace the standard libraries vector with our own vector. Now we still need to use this one in the utilities. So I'm going to turn use STL vector to 0, and that will disable this block for me. Then here I'll include our own vector. Okay, here in script CPP file, we are calling the function erase unordered for the list of entity scripts. And we wrote this function because the standard libraries vector doesn't have an erase unordered function. And to keep things the same as they are right now, I'm going to add a utility function that will use the erase unordered function from our vector. And the next error that we get is a constructor for the vector that we haven't implemented yet. And that's the one that uses iterators to go from the first item in a stream and read it all the way to the last item. And to do this, we can go ahead and look at the implementation in the STL vector. By the way, every time I look at any code in the STL, I need to take a long shower afterwards and cry myself into sleep every night. For 2 weeks. So you better appreciate the amount of pain that I'm willing to suffer for you and subscribe to the channel and like the video if you haven't done so already. So we need to still implement this one. It takes some iterator type and iterates from the first element to the last one, and then copies all the items from the iterators. So this abomination here does pretty much the same thing as what I wrote here. Let's check if everything is still working. We are still using a vector that destructs the elements, although we are using this one, so we need to tell it to not destruct anymore. And all it does is it moves the responsibility of destructing items to the free list instead of doing it in the vector. And no errors this time. And there are no memory leaks, that is also great. And now, if I would go here and go back to the STL vector, then we would get errors. And I would like this engine to be able to use both for people that would prefer using the STL vector. So what I can do is use the STL vector whenever it is enabled and otherwise use our implementation. For example, here we can go ahead and check if STL vector is used. But then we are back to our original problem, and I can try to ease that problem as much as I can, but it will never go entirely away. And the way I can do that is, first of all, by warning the user that they are using standard libraries vector, which is not intended to be used with this free list class. And one more thing that I can do is clearing the contents of each slot to 0. And the benefit of having all zeros in there is that most data types, at least in this engine, have zeros as default values. So if there are all zeros in there, then they can deal with that basically. And there is a smaller chance that that would represent invalid data. Here we set the entire buffer in the array to zeros. And now if we compile, we get these warnings, but we are still able to run the program. And when we close the application, nothing happens. We don't get any errors, while I'll still have this destructor here. So that works. Going back to the reason of all of this work that we had to do, which is the fact that we couldn't really trivially add a render surface in the core CPP file. And then we had to do some kind of hack to destructed, and it wasn't pretty. Like here, we had to call it explicitly to destruct the surface. Now, instead of doing this, what I can do is use a free list to put the surfaces in. And we are still using the standard libraries vector, so let's turn that off. Everything is still working. We didn't get new errors and we don't have any memory leaks either. One more advantage of using this free list in combination with our implementation of vector is that we can do without writing a lot of code that otherwise would have been needed to get a class like this D3D12 surface into a container. In other words, we can use these containers with classes that are not copyable and not movable. And to demonstrate this, I'm going to disable copy and move for this surface class. Now the last thing that I'd like to do is to fix a typo that I made. Here we are checking if the surface is valid twice, but one of these should be the window. And now we have a free list container and our own implementation of a vector class. Thank you for joining me today. I hope that you enjoyed this video and learned something new, and I'll see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!